Can you tell me what solutions Glare provides?
For sure! We provide quite an array of solutions. Let me show you. Here's a great way to arrange your product display. Hi, Sheila!
Oh, hi!
With Planogram, you only need to take a picture of the display and instantly your layout is checked, so you can determine the best layout for your display that can increase sales in a cool way.
Absolutely.
Want to know how you can maximize your inventory? We have demand forecasting, a technology that can predict the demand of your products in the market. Being an integrated system, there will be no more inventory challenges in your supply chain.
It's all connected.
The future is here! With OCR technology, all you have to do is scan your documents, then all physical data will automatically be digitized at your fingertips.
Well, that's fast.
Glare will protect your banking system with fraud detection technology. Suspicious transaction will be automatically detected so that your banking staff can rectify it immediately.
Don't worry, we'll figure it out.
That's awesome.
I know, right? AI is definitely beyond what we've imagined. From face recognition that we use daily for online payments, to vehicle detection in law enforcement, and deep dive analytic for your customer that can help them make accurate decisions.
There's so much more that Glare can do. Let's collaborate and join us in your transformation to the future.
Yes. So we will start from 40?
Yeah, 40 now. Yeah, so ladies and gentlemen, sorry for interrupting your poster session. We have to finish the poster session and the coffee break. So we will continue to the next session, next oral session. Please have a seat and we will start now.
Buddy? Oh, sorry. Hello, sorry. Hello, everybody. I'm Yuan Fu Liang from Taiwan. I'm the session chair of the oral session 3. In this session, we have a 6th paper. And the first paper is, come here. And the first paper is MEASR English code switching speech data set, MEASR. And the presenter is, how to pronounce your name? Andy. Sorry. Okay. And the presenter is Randy. Okay. So let's welcome the presenter to present the first paper for us. This one? Yeah. Wait a moment. Okay, you can test. This one will be online. Okay. Only this one.
Good afternoon, everyone. Before starting my presentation, I would like to thank all committee members for organizing this conference. My name is Teng Ki A, and PhD candidate from University of Computer Studies, Yangon. I'm here today is to discuss about Myanmar English code switching speech dataset MEASR. Let me move to outline descriptions of my presentation. So these are the quick overview of outline for my presentation. Introduction, objective, overview of our dataset, how to prepare dataset, and how to transcription making for the dataset and analysis of the dataset. Last one is a conclusion section. Let me move to introduction slide. Code switching speech is defined as speech which contains more than one language within an utterance. With the developments of globalization, this multilingual phenomenon has become increasingly common in real life and education. So the research on this has attracted growing attention. In Myanmar, some lecturers often use both Myanmar and English, reflecting real classroom dynamic. Not only in classroom, in the real world, we can use the code switching also. However, code switching speech data is scarce, especially in academic and technical domain. So we are decided to collect and analyze bilingual lecture speech data set to support accurate transcription and ASR development. This paper focuses on bilingual as specialized Myanmar English ID lecture dataset MEASR. Now let me go to objective slide. Objective for this paper to prepare a raw transcription for analysis and model development, to examine utterance level statistics such as length and duration, to demonstrate one data set suitable for code switching ASR text with different data analysis criteria, to develop a bilingual speech data focused on Myanmar English IT lecturers, to capture natural classroom speech, including code switching and technical terms, to enable the end-to-end AXR model for bilingual academic content. And then I will discuss about dataset overview. In MEASR dataset comprise 10 hours of speech recording primarily from online IT class and include both monolingual and intra-sentential code switching utterance. Notably, speech contribution from female teachers are approximately 3 times higher than those from male teachers, reflecting the gender imbalance in Myanmar teaching workforce. I think not only in Myanmar, around the world, this rate is like that. As a result, the data set contains a greater proportions of female speaker data, aligning with real-world demographic. The data set includes speech from 10 teachers and age ranging from 25 to 45 years, including switch type X intra-sentential and average speaking rates is 58 words per minute. Now let me move to dataset preparation. We have a 2 sentence type in code switching. They are intra-sentential and inter-sentential. For example, mislingual sentence, morning, တွေ့ရတာ ဝမ်းသာပါတယ် in English is a morning, nice to meet you. That is an intra-sentential. Next one is an inter-sentential. သူလာမလာမသိဘူး but I already invited him. This is a mislingual of Myanmar and English. In English term is I don't know exactly he is coming or not, but I already invited him. That is an inter-sentential. And then we have decided to do intra-sentential because most of the sentences in lecture are intra. The data set contains natural classroom interaction with frequent inter-sentential sentence code switching during ID lesson, recording through personal computer microphone of teacher and student. The MEASR dataset include only the speech utterance of teacher and some of the student speech like "Okay, yes," and "Nale bade," I understand. In MEASR dataset, teachers frequently alternate between language to explain the meaning of individual IT technical terms or to differentiate between similar terms for students. After annotation process with true, generate text file that includes speaker ID, start time, end times, and durations of each utterance. This figure, you can see the sample annotation for ID lecture by using the tools. Next one is transcriptions of the sample data set. In this transcription, totally we have 5 columns. First one is a speaker ID, second and third is a start time, end time, duration. Next one is a transcription. In this first column, you can see the MT01FBX. So MT is a Myanmar teaching, 01 is a speaker number, and F is a female. And then BX is a session of recording B for software subject. Now let me move to data set transcription. In that dataset transcription, our dataset is a MEASR Myanmar English, so the presence of the both Myanmar and English segment in a single utterance. Next one is paralinguistic phenomena like coaching or louching are included, or other non-verbal vocalization included in this data set, because this one is a spontaneous data set. Proper noun or abbreviation, for example, my data set is focused on the IT lecture. So for example, in the website subject, if we want to insert one image in the website, we need to use the abbreviation IMG, so which is a short of the image and is frequently used in IT context. Next one is colloquial speech are included in this data set. For example, who, and so on. And then in my data set, I added the text normalization also. For example, equal to are chained to their verbal equivalent, example, EQUALTO. And then another one is a numeric term, 1, 2, 3 are chained to the ONEDWO and 3 and so on. Now, let me move to data analysis. So our data set analyzed on basis of the following criteria: total number of code switching utterance, distributions of word count by utterance duration summary based on second, and then top 10 English and Myanmar bigram and trigram of our data set, because these tools are important for the language model for our ASR development. So, code switching is predominantly observed in technical discussion, particularly in IT-related content, where a teacher combines Myanmar and English within single sentence. We can see in figure 3, total utterance for 10 hours speed is 11,945, and then missed language utterance is 1,042. So percentage is 68%. So we need to develop the code switching data set for our Myanmar English IT lecture. We decided like that. So in this slide, we can see for the second analysis process, fourth figure presents the distributions of utterance containing fewer than 10 words. Totally 7,882 utterances between fewer than 10 words. And in the figure 5, display utterance with word counts ranging from 11 to 30 words, comprising 3,978 utterances. In this figure 6, illustrates the subset of 85 utterance that contain more than 30 words. Longest sentence is 58 words per utterance. In that figure 7, approximately 10 hours of audio with utterance duration ranging from 0.12 seconds for short command for interjection to 23.79 seconds. Next one is comparisons of the top 10 English Myanmar bigram based on the frequency in the MEASR data set. To analyze lexical pattern, we extract the most frequent bigram, 2-word combination, and trigram, 3-word combination, because this is very important for our language model, preparing the language model. On the left figure, you can see the Myanmar top 10 bigram. On the right figure, you can see the English top 10 bigram. You can see a lot of technical terms, primary key activity diagram, and so on. On the next slide, we will demonstrate the top 10 trigram of Myanmar and English. So left side is Myanmar trigram, right side is top 10 English trigram. According to this analysis, we need to develop the code switching data set for our IT lecture. The most common trigram in both Myanmar and English are shown in figure 9. These words, which are commonly used in online teaching sessions, reflect both general spoken discourse and domain-specific IT terminology. After analysis step, let me conclude my presentation. In conclusion, the MEASR dataset was created to tackle the challenge of Myanmar English code switching in autonomous speech recognition. especially in online IT education. This dataset captures natural inter-sentential code switching from accurate teaching setting. It includes high-quality transcription, language boundary notes, and specific vocabulary relevant to the technical topic. MEASR dataset aims to support the development of code switching ASR system by offering real lexics and varied speech data. In future world, we have planned to grow the dataset with more speakers and wider range of subjects like engineering or medical. We also aim to use it for training end-to-end CS-ASR model and to investigate related texts like language identifications and code switch boundary prediction to improve multilingual speech recognition for our Myanmar. Thank you for your listening. If you have any question, you can ask me freely.
Okay, thank you. Any question? This is a very important topic. Okay, please.
Okay, thank you. So, in the future, I mean on your next work, so which models will you use in the MEASR dataset?
Yes, actually, in the future, I will develop the sequence-to-sequence pipeline ASR by using this data set. For example, I will use the GMM, HMM with speaker-independent transformations, or MFCC with LDA and MLT, and then DNN with different parameter, and then I will develop the end-to-end ASR by using this data set. Thank you.
Okay, we still have time. Any question? Okay, maybe I ask one question, because I want to do the same thing.
Yes.
In our university, we try to transcribe our online tests,
Yes.
AB online tests into translation. There are many technical terms there also. It's the same case as yours.
Yes.
But I think it's a very difficult or labor-intensive problem in your case. So do you have seen about how to do it on something like unsupervised way or some weaker supervised way, or something like knowledge distillation way, something like that?
Okay. So, in my future work, can you ask me?
Okay. I mean, what you have done now is very labor intensive, right?
Yes.
So you have only 10 hours. 10 hours may be not enough to build a good ASR.
Yes.
So nowadays many people use something like knowledge distillation.
Yes.
And so have you seen about something like
Yes,
this?
yes. In the future, I will collect a lot of data. So maybe I think 50 hours or some any other field like engineering or medical subject. I will collect all of the data. I will increase my data set, and then develop the end-to-end model. Now I'm trying the pipeline model, DNN also. But what error rate is a little big. So now I'm trying also.
Okay.
Yes.
Maybe we could cooperate with each other, because we are doing it in the same
Yes.
situation.
Yes.
Okay. Any question? Okay. So maybe we can have some cooperation after, because we are doing it in the same same code switching database.
Yes.
Okay. Let's send the speaker. Okay. Thank you. Thank you. Okay. Okay, next paper is a corpus-based investigation of acoustic feature. Sorry, please come here. Information intelligence of super elderly Japanese speech. And the presenter is you are Mako?
Mako.
Okay, Mako. Okay. So let's welcome Mako to present this paper.
I
It's the next one, the previous one.
pointer?
This one. This one.
This one? This one?
Okay.
No, I want to use point.
Sorry. What is it?
Good afternoon, everyone. And let's start with the program. While we know that speech intelligibility often declines with age, the specific acoustic features aren't fully understood, especially in the super elderly population. This brings us to our key question: what are the key acoustic features associated with reduced intelligibility in super elderly Japanese speech? Our objectives were to clarify the characteristics of unclear utterance of the super elderly by comparing 3 patient groups from Red Speech Corpus. And these groups are cognitive healthy speakers with intelligible speech, CHI, cognitive healthy speakers with slightly unintelligible speech, CHSU, and speakers having dementia with slightly unintelligible speech, DMSU. For this study, we use our ears corpus, elderly adult-led speech. We created and published this corpus to develop automatic speech recognizers. We had 123 participants with mean age of 83.4 years old, including dementia patients. The speech task is reading aloud phonetically balanced sentence, ATR 503 sentences. These are widely used in Japan's speech recognition research. This consisted of 10 sets of subsets. And importantly, each person led different subsets, and there is no common sentence for all speakers. And we have, the speech was 16 kHz with 16-bit resolution. We have the result of the dementia screening test, HDSR, as non-public content. This test is widely used in Japan and offers accuracy comparable to the MMSE. Now let me explain our methodology, beginning with group assignment. We divided our speakers into groups based on 2 criteria: their HDSR score and perceptual intelligibility rating by 10 listeners. After balancing age and participant number, only females were assigned to ensure consistency across groups. 3 groups were examined: the CHI group with 11 speakers with a mean age of 83.8 years, and the CHSU group, 13 speakers with a mean age of 85.4 years old, and the DMSU group, 12 speakers with a mean age of 85.3 years. For the acoustic analysis, we selected features that are measurable from ears speech and provide comprehensive coverage of the phonation process. All analyses were performed using plot. Here's a list of acoustic features we measured. They are presented by category. Many of these acoustic features are known to be affected by aging and some dysarthrias such as Parkinson's disease and ALS. For the temporal dynamics, we measured speaking rate, articulation rate, which is a speaking rate calculated by excluding non-speech intervals, and the frequency of non-speech intervals, or NSI. For the temporal dynamics, we measured speaking rate. For the vocal quality, we assess the smooth capsule peak prominence, or CPPS. We choose this method as robust for measuring laryngeal noise in continuous speech. For vowel articulation, we measure the formant frequencies and their standard deviation, or SD, for all Japanese 5 vowels are I, U, E, O, along with the vowel articulation index, VAI. This metric can detect vowel centralization. Finally, finally, for articulatory dynamics, we use the plosive token and measured those four. Briefly, the F2 slope measures how fast the tongue moves during consonant to vowel transitions, a slower rate to reduced clarity. VOT captures the timing between consonant release and voice onset, important for distinguish voiced and voiceless stop. Finally, the consonant to vowel duration ratio reflects the temporal relationship between consonants and vowels. A lower ratio indicates reduced temporal contrast. Let's move on to our results, starting with temporal dynamics. These participant groups are cognitive healthy speakers with intelligible speech, CHI, and cognitive healthy speakers with slightly unintelligible speech, CHSU, and dementia speaker with slightly unintelligible speech, DMSU. The horizontal line in each box represents the median value, and this.
It didn't work because it is a screen. It did. So the laser point didn't work for this one.
The graph on the left side shows the frequency on speech intervals. The vertical axis represents the number of non-speech intervals per 100 molar. Both SU groups showed significantly more frequent non-speech intervals than the CHI group. And the graph in the middle of the slide shows the vertical axis represents molar per second. The speaking rate was also noticeably reduced in both SU groups. Next is the articulation rate. This was calculated as speaking rate without non-speech intervals. It was not reduced in either the SU group. Moving to the vowel articulation, let's examine the formant variability. The vertical axis shows frequency in hertz. The standard deviations of formant 4 for the vowel E was significantly higher in both SU groups compared to the CH group. The SD of F2 for A was also significantly higher in the DMSU group than in the CH group. In addition to these findings, in the CHSU group, we observed a trend of increased variability in F4 for U. For the DMSU group, this trend was more extensive, with increased variability also observed for F2 in A, and for F3 and F4 in both O and U. Next, I would like to explain the articulatory dynamics result. The vertical axis represents seconds. Here's no significant difference in VOT of plosive token among the three groups. For vowel duration for plosive token, DM speakers demonstrate longer vowel duration than CHI speakers. Additionally, SU groups exhibit a lower CV duration ratio compared to the intelligible group. This slide is the last slide of the result. Notably, several acoustic features did not distinguish between groups. These include CPPS, an index for laryngeal noise, VAI, which are index for vowel centralization, F-slope, an index CV transition dynamics. Let me interpret these findings regarding temporal dynamics. Increased non-speech interval frequency and a slower speaking rate were observed in both SU group. These may contribute to low intelligibility. Among our speakers, lead speech, non-speech intervals are often inserted within words or at other unnatural locations. Therefore, we plan to investigate further how this misplacement affects speech intelligibility. Formant instabilities in both SU groups were greater than in CHI, with DM exhibiting more unstable vowels. Fs reflects tongue anterior-posterior movement, which is essential for vowel discrimination. Then increased F2 variability might affect intelligibility. However, the effect of F3 and F4 instability on intelligibility remain unclear and require further investigation. Regarding to articulation timing, both SU groups showed a decreased C to V duration ratio and a longer vowel duration in DM-SU than CHI. Interestingly, patients with ALS and severe Parkinson's disease also show a decrease in the C to V duration ratio and increase in vowel duration. This parallel suggests that the SU speakers in our study may also exhibit the consequences of precise or sluggish articulatory movement. Let me return to those new results I mentioned earlier. These features are known to detect abnormal utterances in some dyslexia and aging. What does this tell us? The intelligibility declines observed here may not be primarily due to generally breathy or hoarse voice, which the CPPS would capture, vowel centralization, which VAI would detect, slower articulation gestures, which the F-slope would capture, distinguishing between voiced and voiceless stops, which VOT measures. This pattern distinguishes the acoustic profile of reduced intelligibility in the super elderly cohort from other non-speech disorders. Allow me to summarize our key findings. Three main features characterize reduced intelligibility in super elderly Japanese lead speech. First, more frequent non-speech intervals. Two, second, greater vowel formant variability, especially in speakers with dementia. Third, a lower CV duration ratio. And significant new findings were found in these features. So our study has some limitations. First, we analyzed only read aloud speech, which represents a low cognitive load speech task. Second, the sentences weren't standardized across speakers, and we didn't have optimal speech tokens such as pataka. And for future work, we plan to develop a new standardized corpus and collect optimal speech tokens. We are going to use machine learning to predict intelligibility from acoustic features. We also intend to analyze spontaneous speech. That's all my presentation. Thank you for your attention.
Okay, thank you. Okay, any question? Okay, any question about this presentation? I have one small question. You mentioned this super elderly. In your paper title, you say this is about super super elderly.
Super elderly.
So what do you mean super here?
In Japanese criteria, 80, the super elderly people are defined above 80 years old.
Okay, great. So you have one sample is 95 years old already. Okay, thank you. Any question? Okay, just one more question. I don't know what is HDSR. I mean, I know MMSE score, but I don't know HDSR. This one. You use this measurement. Right? Okay, so what's the difference between MMSE and HDSR?
HDSR is made by Japanese doctors, and several questions in HDSR is common to MMSE, and HDSR is consists of 9 questions, but all questions are oral question and oral answer. That's the difference between MMSER and HDSR is more high accuracy than MMSE.
So it's better than MMSE.
Yeah.
Okay.
And the HDSR is widely used in Japan.
Okay. I'm now very comfortable with MMSE. Okay, any question? Okay, due to the time limit, let's thank the presenter again. Okay, thank you. Thank you. Okay, where is the next? Okay, the next speaker, next paper should be prosodically annotated Bailey and Sussman audio book corpus for sentence boundary detection. Is the presenter here? Please come in. So what's your name?
My name is Priyanjana.
Priyanjana. Okay. So let's welcome Priyanjana.
I'm Priyanjana Chaudhary.
Sorry about this. Okay, this is the point. This one. In the slide. Slide is not yet ready. Okay. This is for next page.
This is the next page, and
Yes,
this is
yes.
the first page.
Okay.
Good evening. I am Priyanjana Chaudhary. I am going to present my work on prosodically annotated Bengali and Assamese audiobook corpus for sentence boundary detection. So before moving on to the work, I would like to give a brief introduction on the languages that we've used. So the languages, Bengali, so these two languages are predominantly Indian languages, Indo-Aryan languages. So Bengali is a language spoken mostly in eastern region of India, and it is also the national language of Bangladesh. And it has, the number of speakers are, as shown in the slide, it could be said that globally it could be one of the most predominant large number of speakers. And second language that I have used here, that I've considered here, is Assamese, which is also Indo-Aryan language, which is spoken mainly in northeastern region of India. So both of these languages, they share a huge similarity in phonological similarity, syntactical similarity. For example, let's say, so in Assamese, I say, Kot Gol. Where did it go? Kot Gol. And in Bangla, we say, Kothaye Gelo. So Kot Gol, Kothaye Gelo, and there are many more. As shown here, Ami Bajare Jabo. In Bangla, it's in Assamese, Moi Bajar Loi Jam. So there are innumerable examples which shows that these two languages share quite such similarity that including both these languages gives an angle, it's an interesting angle to think about multilinguality ultimately, that if we are to develop an AI based on multilingualism, so maybe if we start thinking about these two languages which has such similarities, these are the number of speakers. Now the point is that these two languages having such large base of speakers and having such rich cultural and literary base, they are still considered as low resource languages. Now, low resource could be, this term low resource could be quite controversial. To be very precise, they are considered low resource because they have compared to the higher languages like English and Mandarin Chinese, etc., which has specific data sets, annotated data sets for most of the AI technologies. Compared to them, these low resource languages are still lacking. So now the thing is that the speech corpus, we have speech corpuses for Indian languages, but annotated, in-depth annotated speech corpus are on the process. It's rare, it's scarce right now. So therein comes our contribution is that we develop a corpus. So the main spoken documents of this corpus is audiobooks. Why audiobooks? So audiobooks is a read continuous speech. It is a narration, but audiobooks are interesting in the sense that they are a caricature of how a human would speak. So now audiobooks could range from fictional to non-fiction and a lot of source materials. So let's say if there is a novel, so the structure of the sentences will not always be uniform as you could see probably in, let's say, a lecture or a news reading. So in audiobooks, the structure of the information, they are varied, and the speaker who reads these audiobooks, they are they have that, in those narration there are emotive, there are a lot of scope of emotive expressions in those. So that is one primary reason of including audiobooks. Now the challenges of including such spoken documents for this corpus was curation, because for example, like English, we have dedicated huge libraries, let's say for LibriVox and etc. But dedicated corpus for audiobooks or narration are again in on the process, not really prepared and ready. And so publicly available such spoken documents, such audiobooks, for example, in YouTube, let's say they are narrating, they have, there are a lot of recording constraints, suppose. There are a lot of music which is being included, and then the voice, texture and all. So curation was done very particularly so that only single narrative speaker, single speaker was narrating the entire audiobook, so that processing could be easier just for that purpose. Later on, perhaps we could use multi-speaker. So for now, so we chose spoken documents which had no background music, so that again pre-processing complexity was reduced, and less noise, and single narrator. So now how the segments, so the spoken documents were annotated based on the utterances, they were bounded. So how do we define an utterance? An utterance is a voiced segment which is bounded by two non-voiced segments. For example, in the first image, A is the utterance. It is bounded by B and C, that is the non-voiced segment. So that is this particular segment is a continuous red segment is an utterance. Now this utterance can be labeled as, there can be two types of utterances. Like for this context of work, we took it as two types of utterances. So a particular utterance could be the end of a sentence. For example, in the second image, the 002 and 003 was a part of an entire sentence based on the source material, the text. So 002 and 003 was a sentence, total sentence. Now the segment, that is 003, that the segment, it was the last utterance, like it was a sentence ending. The utterance was ending the sentence. So that was annotated differently. It was annotated as like, that was marked as ending, so it was marked as S. Like this utterance is the end of the sentence, and the rest of them were annotated as, rest of the utterances were annotated as PH. And then there was and the non-voiced segments were annotated as P, which were the pause regions. This was how the utterances were arranged. And there are some few words, the words are also annotated for each of the utterances. All of these were done based on the source text that was available. And number of peaks of the intensity curve, the energy of this utterance, the number of peaks were counted, and behavior of the pitch curve and the energy curve was also recorded as in, was also considered here. So there was, so for each word, if the word is rise and then falling, so the word is like why, so that rise to fall, so that those intonation, those behavior of the pitch and the intensity as well, they were considered here, and they were annotated for each word. So a brief overview of this entire corpus. So this is, so the size of this corpus, of course, is in the smaller region. So this is approximately 9 hours. It's a little over 9 hours, let's say. And the speakers were from like 9 females and 5 males. So from the pie chart, like a certain balance was maintained, like it was attempted to be balanced in terms of gender data and in terms of language data. So this entire data set and this entire corpus, to validate these annotations, so we ran a small pilot study. So we considered a sentence boundary detection problem. So in this case, to elaborate, sentence boundary detection was considered, like two approaches were just briefly studied. One was a pause duration threshold method. So this was taken taken from the references of two previous works. They had done that. Suppose if a certain, suppose a sentence has ended, and that after that utterance, the duration of the pause segment was calculated, and based on that, it was considered that whether that particular utterance is really the end of sentence or not. So that was one baseline. And another baseline was considered, which was like any pause duration, that mean of that any pause duration, the non-voice segments, whatever the value was found. So that was another baseline. These are the very basic baselines to find out, like it was an intuitive idea that how we really consider final and sentence ending utterances. And the threshold value, these threshold values that is given as baseline A and B are as such based on what we found from all the audiobooks that we had collected. Now the method that was explored in depth was a binary classifier based sightness boundary method. Basically, so that we saw that there is two kinds of utterances, which is a sentence entering utterance and which is not a sentence entering utterance. So we took the features like the acoustic features, the kind of the duration of pause, which is bounded by both of them, and those were the features, and they acted as the attributes. The labels were S and PH, like whether it's ending the sentence or not ending the sentence, and a simple binary classifier was evaluated on that. A random forest-based classifier was trained on that. And the summary and the performance was as such. So for the baseline, which was like just the threshold of pause, which was the mean pause of every ending of the utterances. So it's like kind of a brute force method. Baseline A and baseline B was a brute force technique. So they had these accuracies as shown. But the model, this classifier, when they worked only in Bengali data, they gave 80.14%. That was the percentage, and the first confusion matrix is for the Bangla performance. And when it worked only on Assamese, when that model trained on the data, and when they worked on new data, when they so 80.38, but the interesting thing to note is that when that model trained, when that model trained on those data, when it was given a test data of both the mixed languages, so it performed well and it worked well. So multilingualism, like a model, it worked out, and the second confusion matrix is for the multilingual model. So basically, to summarize this entire work is that as to key contribution is that this corpus was made, but the primary objective is the primary point is that this is just a fundamental idea that this kind of work can be done based on a prosody-based modeling, which can be text independent, basically designed for low resource languages. Something like that can be carried out for any kind of languages, and it can be expanded for more type of languages, and more, it can be included like more speakers and more types of spoken documents can be introduced. So this is just a foundational idea. And yes, the limitations is like, its glaring limitations is that yes, the corpus size is very small, but then the depth of annotations has been like 10,000 utterances, and they have been annotated prosodically, and so that was maintained. And methodology simplicity of sentence boundary direction, yes, again, but then this was considered as a pilot study, so this can be further expanded for better models, neural models further. So these are the references. Thank you so much.
Okay, thank you. Okay, any question? Yeah, please.
Good evening, ma'am.
Good evening.
So my question is, when you are saying that you are giving both the languages together, so is there any overlap, or you are not considering?
Overlap as such, like there is no code mixing.
Okay.
There is no code mixing.
So there is, the sentence is full utterance.
Yes, yes.
Okay.
So for example, in a data set, one data set we've considered was that only Bengali sentences. But then when I'm talking about both of them, the data set had Bengali sentences and Assamese sentences. So when we look at the data set, it's not really the sentence that we are looking at the structure of how the acoustic data. So it's ultimately just how the speaker, how it was, represented.
So one is Bengali, another one is Assamese,
yes.
then again Bengali,
yes,
Assamese,
yes.
like
this.
this.
It was balanced and all.
Okay.
But the point was that it was like that phonological similarity, the way both Bengali is spoken and Assamese is spoken, that similarity was that was taken into consideration. Like that was like, maybe that helped this. Maybe this can be more, this inference could be more solidified if we try Hindi later.
Right.
Once we try Hindi, because, and other step by step other Indian languages which has similarity with Bangla and Assamese. So that was the main idea. Yeah.
Thank you.
Okay, just one, any quicker question? Okay, please. Yeah.
Prosodically annotated.
Yes.
So why do you call it prosodically annotated? I didn't get that.
Yes,
point.
so just for the time being, the intonation, for each words, the rise, fall of the both pitch and energy contours are being recorded, and also the data set that it ultimately generates is we are taking into the pitch values of each of the words, and then the utterance pitch values we are taking the.
So the annotation contains any information about whether the pitch contour is rising, falling.
And the
Yeah.
pitch, the raw values of them, sir.
Yeah, okay.
Yes, pitch, intensity, and the number of peaks of the intensity. So it's just small set for now. Yeah.
Okay. Okay, now due to the time limit, let's send the presenter again. Thank you. Thank you very much.
Thank you, sir.
Okay, we have to move to the next paper. The fourth paper will be presented online, so we will key in the last one. So now let's move to BK380, automated assessment tool for K3, Bangsamoro education. Where is the presenter? Sorry. Okay. Is the presenter here? For paper ID 85, is the presenter here? Oh, okay. Oh, sorry. Okay, sorry. So I don't realize that this one is also another presentation. Okay. So can you hear me? Oh, okay. So this is a video recording. So let's. Okay. So let's play the recording.
Everyone, I am Francis Santelices from the University of the Philippines, and on behalf of our team, I will present our work entitled BK380, an automated assessment tool for K-3 Bangsamoro education. This will be the outline of our presentation for today. For the background, in 2021, the World Bank reported that the Philippines is among the worst in East Asia and the Pacific in terms of learning poverty rate. 9 out of 10 Filipino children were unable to read and understand age-appropriate texts for 10-year-old children. This is a very alarming statistic since reading and comprehension are the foundations of learning more complex concepts and communication in general. Furthermore, in the Bangsamoro Autonomous Region in Muslim Mindanao, or BARM, there are already several challenges. A few of them are the teacher-student ratio, limited access to computing machines and internet connectivity, and areas in BARM are geographically isolated and disadvantaged. To address this problem, the Bangsamoro K-3 Assessment Tools, or BK380 project, was launched through the funding of the Australian government through Education Pathways to Peace in Mindanao, or Pathways, in partnership with the Department of Education and the Ministry of Basic Higher Technical Education, or MBHTE, and the Readability Center. BK380 aims to aid K-3 educators and learners in automated assessment and recording and monitoring the progress of learners in the domains of numeracy, socio-emotional learning, and literacy. BK380 has 2 versions, the pen and paper and the digital version. For this presentation, we will focus on the BK380 Digital. It is a standalone Windows app that has a scoring feedback mechanism and a built-in speech recognition tool. For children's speech recognition, The ASR, or Automated Speech Recognition System in BK380, is used to provide quick and standardized feedback. However, developing ASRs for low-resource languages, such as the Philippine languages, remain a challenge, especially for children's speech. To obtain more data, there are several options we can choose from. We can either do adult voice pitch modification, use a self-supervised model training on adult data, and transfer learning. For our work, we choose to fine-tune a self-supervised model. However, to do this, we collected several speech recordings from children in different regions in BARM with the assistance of their learning facilitators and teachers. To start the development of the ASR system for BK380, the BK380 Children's Corpus was developed. It was developed to serve as the baseline data for the ASR and miscue detection system of BK380. It consists of words, phrases, sentences, and passages listed in increasing difficulty. Prompts were also ensured to be at least for grade 2 and grade 3 students. The corpus consists of Filipino, English, and the 8 mother tongue languages in BARM: Bahasa Sug, Chabacano, Iranun, Magindanaon, Meranao, Sinama, Teduray, and Yakan. As for the data collection, consent from the parents, the students' parents, were obtained pre-recording. We also developed a recording tool based in Flutter to make the data gathering portable for the teachers and learning facilitators that will be helping us. Also, since different teachers and learning facilitators will handle the data collection, we standardized this by having an online orientation /training for the teachers and providing recording kits so that every data collector would use the same type of equipment, have the same app versions, and have the same prompts. In summary, the BK380 Children's Corpus has 122 hours of Filipino children's speech data across 10 languages. This includes 24 hours of English and 45 hours of Filipino recordings. The BK3 test areas were designed to evaluate each individual student's capabilities and areas needing improvement. The data from BK380 helps the teachers plan interventions to address learning gaps. Specifically, the test areas are the following: numeracy, social-emotional learning, and literacy. These are the corresponding subtests within each test area. As for the app itself, the backend was developed using Python and uses WAV2Vec2 with unsegmented speech labeling for fine-tuning. A cross-lingual speech recognizer XLSR53 English which demonstrated improvements on low-resource datasets. Specifically, it was Jonatas's implementation on Hugging Face that resulted in a word error rate of 7.33% on the Common Voice 11 dataset. Currently, only English and Filipino speech models are available on the BK380 backend. We fine-tuned the XLSR53 English using the English and Filipino subsets of the BK380 corpus and integrated CanLM for the English prompts to improve the word error rate. For the Filipino Children's Speech Recognizer, an English-Filipino speech topic tagger was fine-tuned on an open-source daily use speech Filipino dataset. The baseline word error rate is 26.8%. From there, it was further fine-tuned on 0.24 hours of training data from the BK380 Filipino subset. For the results, the original XLSR53 English model was tested on 5.86 hours of the BK380 English subset and got a word error rate of 47.49%. With the CanLM language model, the word error rate improved to 33.31%. The Filipino baseline model was fine-tuned using 0.236 hours of BK380 Filipino subset and tested on 14.71 hours of the same subset. Results show that the language model boosting improves the word error rate. As for the front end of the BK380 Digital, we designed it to work in areas with limited to no internet connectivity, so it's standalone. It's developed for Windows using Flutter. Windows is the main OS on devices being provided to the teachers in BARM. The ASR backend is also in the app, and design-wise, it follows the MBHTE branding colors as shown in the next slide, right here. This is the login page of the BK380 Digital. The BK380 Digital also has several features. For classroom management, we have a page for adding and editing information of students that the teacher is currently handling. For the subtests, each main test area is broken down into subtests. Contents vary per grade level in terms of number of question and the type of subtest. These are screenshots showing the dashboard of showing the main test areas and the subtests of the numeracy for kinder, as shown on the right, figure 8. Tests contain both textual and visual guides. For SEL, images were generated using AI, including Bing. These are thoroughly curated to ensure a diverse and inclusive pool of pictures. For the listening and oral tests, audio control are shown on the screen. Other input modes or question types are multiple choice and check and X buttons. Also shown here in the bottom is a progress bar and navigation buttons on the side to navigate through the questions. For score evaluation, BK380 uses answer keys and built-in ASR for the oral miscues. Subtest summaries are generated after the subtest completion, as shown here on the right. Results are stored per student and are viewable via the teacher admin page as shown here. The BK380 Digital also generates an exportable student performance report containing detailed scores, descriptive performance rating, and recommendations, and charts showing that how the student stands relative to his or her class. We also conducted a usability test with BARM teachers around March of last year. We standardized the test by creating a script that automatically installs the app and collects feedback from the teachers. Majority of the feedback stated that the users found the BK380 Digital convenient and easy to use despite having a slight learning curve. The teachers say that the app significantly reduced manual checking and paper forms. Overall, the app was well received and is planned to be officially rolled out by the MBHTE this year. To conclude, we developed BK380 Digital, an automated assessment tool. It covers three main test areas across Filipino and English and includes an automated literacy module via an fine-tuned ASR model with language model boosting. For the future, we plan to expand the ASR to include the 8 BARM mother tongue languages, improve ASR performance further, and add tutorials and UI improvements for better user experience. A BK380 Lite for Android could also be considered for wider accessibility. We would like to thank the MBHT BARM Pathways with special mention to Ma'am Bona Luder, DFAT Australia, the Readability Center led by Mr. JC Pascual, and the BK380 team, the technical team, and the content team. Here are references. Thank you. Maraming salamat po.
Okay. Okay. Could you hear me? Yes. Okay, great. So, any question? Okay, I have a quick question. I noticed your error rate, ASR error rate is quite high, something like 50%. Do you have any comment about this one?
Actually, the car experience are not yet exhaustive, as this is an initial version of the ASR we're trying to implement. We plan on improving, gathering more data in the future if permitted by the project to improve the ASR. What we wanted to do in the experiment is just to show that language model boosting improves the work area.
Okay. Any question? Maybe I ask a little further because the error rate is quite high. So I mean, since the error rate is quite high, so how do you give the feedback to the student?
So right now it still functions as an augmentation to the teachers that are using the assessment tool. It's not completely what do you call this? Autonomous yet. It's
okay.
not automated, but our goal is to make it that way in the future.
Okay, and you have tried some approach to build a ASR for children. So which one is the best one? You mean something like the transfer the adult ASR model to student, or something like shift the picture or something? Which one is the best approach?
Sorry, the sound is quite loud on my
Okay, it's my fault. I mean, you mentioned you try several different methods to build the ASR for children. Something like change the pitch, or something like transfer learning. So which one is the most effective one?
I think based on our context, which is that the Philippine languages are low-usage languages, the fine-tuning of supervised, pre-trained supervised model is still the best way to go.
Okay, thank you. Okay, due to the time limit, let's send the presenter. Thank you. Thank you. Okay, let's shift the paper ID 5, the affair of question, intonation, and focus, a comparative study on Tianjin Mandarin and American English. So this is also online, or where is the presenter?
Yes, the presentation is on.
Oh, okay. Okay. So you, could you hear me?
Yes.
Okay, so please start your presentation. Thank you.
Okay. Could you see this mic?
Not yet.
Not yet.
And you have to switch it to the fourth screen.
Yes.
No, not this one. You have to share the other screen, not this one.
Yes. Okay.
Okay, great.
Okay, thank you. And now let's start. Good afternoon, everyone, and we're Sean from
Okay, any question? Okay, can you hear me?
Yes.
Okay. Okay, you have so many data. So can you give a brief summary about what's the difference between Tianjin Mandarin and American English and this on your study?
Pardon, in my study, what is about Tianjin Mandarin and American English that I did here goes back to previous before the Tianjin Mandarin.
Okay. Sorry. I mean, you mentioned there are some universal character. They are the same in Tianjin Mandarin and also American English, right? But what's the major difference between these two dialects?
Oh, okay, I got it. The major difference between Tianjin dialect and American English, and you can see from this, American English relies more on duration cues to focus and the voice recognition. And it records the loss of post-vocal compression, but get post-focus and pre-post-vocal cues. But in Tianjin Mandarin, post-focus compression still exists. And also, there are some data about it, and it relies more on pitch cues. And so, so this is my answer.
Okay.
Yeah.
Okay, thank you. Any other question? Okay, due to the time limit, let's move to the next paper. And let's thank the presenter again. Thank you. Okay, thank you. Okay, let's move to the last paper. Okay. The last one is Vienna speech database for non-reference telecommunication quality assessment. This is also an online presentation.
If you hear and receive my slides?
Yes.
Recording stopped.
Okay, so you can.
Recording in progress.
Okay, if you are ready, you can start your presentation.
Hello everyone. Thank you for joining us today at O-COCOSDA. My name is Oli, and I'm delighted to present our paper, Vietnamese speech database for no-reference telecommunication quality assessment. This research was a collaborative effort between me and my co-workers from Dutch and Thailand. So, as we all know, speech quality is critical factor in modern communication systems, as it directly impacts user experience and consequently the reputation of service providers. Due to this, we have speech or telecommunication channel assessment, quality assessment, which takes the input signal from the receiving end and calculates the desired quality score, typically on a scale of 1 to 5. And with millions of calls made worldwide every day, there is a clear explicit need for automatic methods to assess speech quality. This is crucial for telecom corporations not only to monitor and ensure a high-quality service for the customers, but also to benchmark and compare the quality of different telecommunication systems so that they can choose which to use in real time. Well, the challenge, however, is in how we measure this quality score. For traditional methods, like in the industry, standards such as FOQA or the use of third-party like mobile are all full reference. This means they require access to both the original signal, pre-reference signal, and integrated the signal received by the user. And this approach has a couple of problems. First of all, it is very expensive to deploy, especially when telecommunication and corporations are third-party, like mobile, often require low measurement
So next we have our data collection process, which was quite systematic. First, we prepare our reference material, and this was a diverse set of pre-recorded Vietnamese speech sample, which is clean, of course. We include studio made. We included in this data set both male and female speakers of different ages, and more importantly, cover different Vietnamese dialects, namely North, South, and Central Vietnam, and other phonetic characteristics. Second, we performed the transmission and measurement. We first transmitted these samples by putting them through standard voice calls on real telecommunication networks. At the receiving end, the Nemo Handy platform recorded the audio and automatically computed the POCUS score in other logs, of course, by comparing the received audio to the original. And to ensure that our dataset was realistic, we had to capture the full spectrum of real-world telecommunication conditions. First, we conducted our collection campaign across diverse environments, primarily in Hanoi, Vietnam, the capital city. As you can see in the table, our scenarios included urban mobility, which is a continuous movement along major streets such as cars and motorbikes to capture handovers, which is the noise of outside the world. Next, we'll have the vertical mobility, which are the measurements that are made during elevator ascent and descent. We also have the challenging penetration, which includes measurements from areas underground, like basements and parking in garages. We also included indoor environments like offices and malls, and finally, we have public transports, like including buses and metro systems. And the final results that we have is our VTQA dataset, containing roughly 6,700 Vietnamese speech utterances, each one labeled with a precise POQA score that we yielded from the Nemo Handy framework. Okay, next let's talk about the model. For our no-reference quality assessment model, we adopted the NISQA architecture as our base. NISQA stands for Non-Intrusive Speech Quality Assessment. It's the deep learning framework, deep learning model, that is pre-trained on a large corpus for many different speech quality tasks. And as shown in the diagram, it uses a combination of CNN layers, a self-attention mechanism, and an attention pooling layer. And this allows it to effectively capture both the local spectral patterns and long-range temporal dependencies in the audio, which are all relevant to quality. For our strategy for adapting this model included two steps. First, a correlation analysis to see which assessment tasks correlate the most to our task. And second, we transfer learning this model by fine-tuning to get our final model. The pre-trained NISQA model provides predictions for multiple quality dimensions, which can be seen in the table. And these dimensions include first the noisiness, loudness, coloration, discontinuity, and an overall MOS score, which is mean opinion score, with relevance to our task as presented in our table. So our first step was to see which of these dimensions correlated the most strongly with the POQA scores in our dataset, which are specific to telecommunication issues like packet loss and handovers. So to evaluate our models, we use two standard regression metrics. The first is the root mean square error, or RMSE. This measures the average magnitude of the errors between our model predictions and the actual POQA scores. For MSE, a lower value is better, as close to zero as possible. The second metric that we use is the Pearson correlation coefficient, or the PCC. This quantifies the linear relationship between the predicted and actual scores. For PCC, a value closer to 1 is better, as it means that our model's predictions correctly rank the quality of cost relative to each other. Let's go to the results. First, here are the results of our initial correlation analysis. This table shows the performance of the pre-trained SQA model when used directly on our BTQA dataset. As you can see, the MOS or mean opinion score and discontinuity dimensions shows the strongest correlation with our whole QA ground truth, as can be seen in the 2 lines in bold on the table. And this makes sense because the MOS captures the overall perceived quality, and discontinuity is highly relevant to telecommunications as it measures interruptions and characteristic, packet loss, and handovers. Based on this, we decided to fine-tune the SQA model, focusing on these 2 tasks. And here is our final results. This table compares an initial pre-trained task with our new models, 1 trained from scratch on our data, and 2 fine-tuned models on discontinuity and MOS task. The benefit of transfer learning is really clear. The model trained from scratch achieved a PCC score of just 0.828, which is much lower than our fine-tuned models, including the fine-tuned MOS and the fine-tuned and discontinuity. However, our fine-tuned models achieved the best performance overall with the lowest RMSE of 0.326 on a scale of 5, of course, and the highest PCC at near 0.886, right? So, and this substantial improvement shows that our fine-tuned models predictions align very closely with the standardized QA measurements. And with this high correlation and low error, the model is ready for large-scale quality assessment. So to conclude our work has successfully built the BTQA, Vietnamese speech database for telecommunication quality. And using this, we developed a no-reference AI model that accurately predict call quality without needing the original signal. And most importantly, this enables a practical framework for real-time, scalable, and cost-effective quality monitoring on 100% of calls, which is a significant advantage over traditional methods. And for future work, we plan to integrate even more advanced SQA techniques, such as ranking-based loss function scoring, or maybe no reference or non-matching reference speech quality assessment, and to further improve performance specifically for Vietnamese networks quality assessment. And that's the end of my presentation. Thank you very much for your attention. I will be very happy to answer any question. Thank you.
Is already a very good pre-trained model. But after you use your VTQA database, you got geometric gain on PCC and RMSE. Could you give some insight about what's the difference between the environment of the pre-trained model and the environment in telecom environment in your country?
Actually, the difference between the pre-trained SQA model and the model trained on our dataset lies in the difference in the 2 datasets that we trained from. For the SQA original dataset, which includes like 78,000 70,000 hours or so of speech, they include so many tasks. And different types of languages, like mostly English and not other languages like Vietnamese does. The problem of Vietnamese is that our language is really tonal and not like not like non-tone, like in the case of English. For example, we have different words like o, and which are all tonal words, which plays a major role in transmission. And these kinds of things can make the pre-trained model performs not too well on our data set, I suppose.
Because your language is a tonal language, not because the in telecom environment in your country are different. Am I right?
Sorry, I forgot to add a little bit more on that. And there's another thing, like many noise patterns that were prevalent in the original NIST QA corpus are synthesized, not like us. We are primarily focused on some types of noise that are prevalent in our telecommunication and environment and throughout our city, or like as I presented earlier, we have other conditions like basement, indoors, outdoors, everything. Like that are much more prevalent in our daily calls than the other types of noises, like white noises and things that are prevalent in the original data set, I suppose. Thank you.
Check. Okay. Yeah, so ladies and gentlemen, that's conclude our third oral session. We would like to extend our appreciation to Professor Leon Fu for guiding this session, and to all presenters and participants who join us here and also through Zoom. And this brings us to the end of our program today. Before we close today's program, we would like to share a reminder about tomorrow's agenda. So tomorrow will take place here also in the Koinonia Auditorium. And please note that tomorrow agenda will begin with a keynote speech by Dr. Nancy F. Chen at 8:30 a.m. And the activities will continue throughout the day and conclude with the gala dinner until 8:30 p.m. So we kindly request all participants to be present on time to ensure the program runs smoothly. And is there any additional announcement from the committee? No? Okay. So thank you very much for your attention and participation today. We wish you a pleasant evening. Enjoy Yogyakarta. See you tomorrow and God bless you. Thank you so much.
Jakarta, yuk, berangkat sekarang yuk, Jakarta yuk.
Hati-hati ya.
Ibu baik-baik di rumah ya Bu. Pamit ya.
Selamat pagi Bu. Selamat pagi Mbak. Pagi Pak.
Ini adalah kisah kami tentang harapan dan mimpi akan sebuah tempat yang penuh kemajuan dan inovasi. Kami tak hanya menuliskan barisan kode dan coretan tanpa arti, tapi solusi nyata untuk berjuta kehidupan setiap
So
hari.
additional announcement for the participant who stay at the Art of
sebuah warisan, dan kami bukan sekedar talenta. Kami adalah penulis masa depan. Kami percaya masa depan teknologi harus dikuasai negeri sendiri dan dibangun oleh anak bangsa yang berani bermimpi.
Fokus untuk tenaga-tenaga ini. handal di bidang science, technology, engineering, dan mathematics.
Dan ini bukan sekedar tempat kami bekerja, tapi juga wadah untuk belajar dan membuka cakrawala dunia. Tempat kami menggantungkan harapan, memberi layanan, dan membangun jembatan masa depan. Karena inovasi tak hanya untuk hari ini, dan masa depan bukan soal garis tangan. Dan kami percaya kemajuan teknologi tak selalu tentang kecepatan, tapi juga soal keberpihakan. Kepada segenap rakyat Indonesia, kami percaya pasti ada jalan, bukanlah sekedar slogan. Dirgahayu Indonesiaku, dari kami, karya anak bangsa yang berjuang untuk Indonesia.